Okay, I think we should get started. This is our last session, the third of the Leading Edge series. We've got 5 talks. And yeah, let's get going. So we're going to be hearing from MacKie about geology and photography of the Alpine Basin.
Well, it's great to be leading the third edge. I go by MacKie, I'm at Stanford, and I'm a student, so judge away. And this talk is going to be about taking bathymetry and radar bed measurements and using that to create a realistic bed topography that we can use to make geological estimates. And my study area is in the Amundsen Sea embayment. And I know that this is an important area because my mom likes to send me news articles, and they're almost always about Thwaites. But in all seriousness, there's a lot of uncertainty about how Thwaites is going to behave in the future. And a lot of that uncertainty depends on what you use as your basal drag, as Byron Persic has shown us. And a big part of that is the subglacial geology. So this project is inspired by a lot of studies, such as this one, that use radar measurements of bed topography to look at the roughness and try and use the roughness to distinguish between sediment and bedrock. And in this talk, I use sediment and bedrock pretty loosely to mean deformable or undeformable bed. But there are 2 issues with using this approach. The first is that you get these crossover errors in roughness because roughness can have a directional component. And the second issue is that we don't know what cutoff point for roughness we can use for saying this is sediment or this is bedrock. So in this talk, I'm going to address both of those problems. So for the crossover error, the easiest solution is to have 2D bed topography. But we don't have that from radar, so we have to interpolate between radar bed measurements. And the most common form of interpolation is creating or spline interpolation, which is used in BedMap 2. And the problem with that is that it smooths the bed, so we can't use it for roughness estimates. So what we need instead of creating or spline interpolation is conditional simulation, where we try and capture the roughness in our bed maps. And so it happens that the only bed simulation I'm aware of by John Goff is in the Amundsen Sea embayment. And what he did was he took radar bed measurements and then said, I think this area should have this roughness, so when I interpolate the bed, I'm going to assign this roughness to it. And that gives you a much more realistic bed parameter, but because roughness is an input into the simulation, you're not getting an unbiased estimate of what the roughness is. So you can't use this roughness for estimating sediment or bedrock. So we need a conditional simulation interpolation mechanism that doesn't require a pre-parameterization of roughness. And so the method we use is called multiple point direct sampling, which is a technique that's most typically used for reservoir modeling or subglacial hydrology, but it's well suited for any subsurface problem. And how it works is that you have some unknown region with some hard data or known measurements, and you use your measurements as training data to simulate information in the unknown pixels. So this sort of allows you to fake it till you make it. And how it works is that, say you want to simulate this pixel here, you've got like a black, white, black Oreo pattern next to it. And what you do is you search your training image for another Oreo, and you can take the pixel next to it and drop it in this spot. So you're searching the training image for places that match your existing hard data to pull values from nearby to fill in the blanks. And as a side note, earlier this week, our group had to play charades, where we had to act out each other's research topics. And I put direct sampling in a hat. And It did not make me very popular with my group, but it was really entertaining. But back to the simulation. This is our hard data. For the Amundsen Sea, we have seafloor bathymetry information, we have a lot of radar bed measurements. You'll notice we have nothing under the ice shelves. But the problem with this is that this isn't sufficient training data for the direct sampling simulation. And that's because we have that radar line problem again. So it's really hard to see how the data varies in 2D. So we turn to Arctic DEM for supplemental training data. And I chose this deglaciated area in Siberia because it has mountains, channels, basins. It's got a lot of topographic features for us to search for that would match the hard data in our simulation. So we start with our hard data. We use direct sampling to simulate bed topography. And so this gives us a statistically realistic bed. Okay, so we've solved the first problem. We've gone from line measurements to 2D bed. And now we need to solve the second problem, which is deciding which roughness is sediment and which roughness is bedrock. And so for that, we turn to the paleo record. So, well, as you can see, we can do multiple realizations of this to quantify uncertainty. And that gives us a more realistic channel morphology as compared to BedMap 2. And the biggest differences are going to be under the ice shelf. But when we look at the seafloor, there's this well-known sediment to bedrock transition that we know from acoustic data. And we can use this as training data to set our sediment and bedrock threshold. So what I did was I pulled a spot from the sediment section and the bedrock section. And then I calculated the roughness for each of those. And how we calculate roughness is that for every pixel, we look at approximately a 5-kilometer window around that, and we calculate the roughness energy, which you get by integrating over the power spectral density curve, which you get by taking the Fourier transform. And if that doesn't mean anything to you, all you have to know is that bigger numbers are more rough and smaller numbers are smooth. So if I plot this as a histogram, I see that the bedrock values have a very high roughness, and the sediment has a much lower roughness. And so you can imagine that if in our simulated bed topography we have a very low roughness value, then it's going to have a very low probability of being bedrock and a high probability of being sediment. And so we calculate this using logistic regression, which is a binary classification tool. And what we get is a map of probabilities of being bedrock. So here, purple 1 is bedrock, and the turquoise is sediment. And so our first order observation is that the seafloor is sediment, in case you weren't sure. And as we get closer to the grounding line, things get a little more interesting. We see the sediment to bedrock transition that we already knew about. Thwaites Glacier here is a little more bedrock towards the grounding line. And as you get into the main trough, there's a predominantly sediment floor. And this is interesting because it matches quite well with ice velocity in the main trough. And you could use this to kind of gain insights on what the processes are here or how the bed is controlling surface processes. There's also this kind of sediment spot back here, which is close to the onset point for a lot of the Ross ice streams. So in summary, we have gone from sparsely sampled bed topography measurements to a continuous bed topography map that we can use to get a geological map. And this, this has implications for uncertainty quantification. We can generate multiple realizations of this and use them in ice sheet models. This allows us to use the paleo data as a constraint. And we can also imagine using the sediment distribution beneath the ice to interpret ice sheet history, or as a constraint for what the marine sediment was like in the past. And what I plan on doing next is
I'm having trouble with the connection.
Nice.
what I'm doing next is generating more realizations of this so we can properly quantify our uncertainty. I'd like to use this in an ice sheet model to determine my basal drag parameters, and we're also looking into using additional data or physical models as training information for better constraining the subglacial geology. Thank you.
Thanks, MacKie. Let's hold our questions till the end of the session. Now we have Nick Holschuh, who's going to be telling us about slowdown of Willen's ice stream.
Thanks, Barry. So, for most of my postdoc, I have been working towards pushing the boundaries of what we can observe in the ice sheet system. Most of my research is focused on radar, and so that's looking at the subsurface characteristics, trying to work towards three-dimensional mapping of the ice sheet bed. But in addition, I've been warmly welcomed into the altimetry community by the ICEAT2 land ice group, and so I've been working with ICEAT2 to try and better characterize the surface. Most of the research I've been doing up to this point has been looking at those two problems separately. Better characterization of the bed in some cases, better characterization of the surface in others. And I was looking for problems where I could try and integrate these two methods together to do something really powerful. It turns out Willen's is a really great place to look at both the bed and the surface to understand the process. And to get at why that's the case, I have to walk through some of the history of our understanding of Willen's. As Helen pointed out, there's a ton of information that we've learned, this community specifically in the past decade, that have really informed our understanding of how the cycle coast ice streams work. Christina Holbe and Doug McHale and many others did early modeling of this system that showed that these ice streams are prone to cyclic behavior. They thin, as they accelerate, they'll thin, it moves that cold ice surface towards the bed, and eventually they'll end up freezing at the bed, slow down, and thicken again. So there's this tendency towards cyclic stagnation of these ice streams driven by the thermal structure, the basal thermal state. That's the large-scale understanding of what's going on at Willen's, but there are all kinds of smaller-scale processes that dictate the overhaul behavior that this community has been studying. Grace and Paul and Slavic and many others have been looking at the seismicity of Willen's ice plain, because this area is really, really flat, and much of the motion that occurs in the downstream region is controlled by this unstable slip. So if you're going to try and characterize the behavior of Willen's, you really need to understand what's going on in these unstably sliding regions. In the early 2000s, Ian Jochen did both modeling and observation studies to try and understand Willen's specifically. And he presented these early observations of the slowdown of the Willen's ice plain. We were starting to see that Willen's is already moving towards this shut-off process that had been hypothesized in the past. And one of the possible mechanisms for that is actually freezing onto the base, as was predicted. So Ian had done an inverse calculation for the distribution of basal freezing and basal melting under the Willen's ice plain, and he found that largely under Willen's, it's prone to freezing. But what he said is, freezing may dewater and strengthen the till if insufficient water is produced beneath the ice stream's tributaries, or if that water does not distribute that water sufficiently, or if the basal water system doesn't distribute that water sufficiently. So in all of these areas where there's an energy deficit, where it's prone to freezing, if you can't bring in water from upstream, the base of the ice stream is prone to freezing into the till and shutting off. So there's now this trade-off between there's an interaction between the basal thermal state and the hydrology under Willen's. As Helen and Sasha and Matt have spent a lot of time characterizing the complex subglacial hydrologic system under Willen's. Obviously, we have this network of subglacial lakes that spatter the ice plain that are connected by a hydrologic system that's driven by very shallow hydrologic gradients. So in other areas where the ice surface slope is steep, you end up with these really dominant water pathways. But at Willen's, where the surface slope is quite shallow, it's prone for reorganization. So understanding how that water from upstream is making its way towards the seismic area will be really important in understanding how that system will evolve. And finally, there's this large-scale interaction between all of the different ice streams on the Cycle coast. Early on, after Cam ice stream shut down, there was this hypothesis that water piracy from the upstream catchment, essentially water that used to feed the Cam ice stream, is diverted into the Willans ice plain. And so, in favor of shutdown of Cam, you end up diverting more water into Willans, which might facilitate fast flow. So, in all of these situations, it's really important to understand the ice surface and ice bed topography, because the geometry of the system is really one of the controlling factors for the basal thermal state and for the hydrologic routing. As Sasha pointed out in a paper in 2012, there are situations where really small changes in the ice surface, only 2 meters, can start routing water down totally different hydrologic pathways. And so we need to know with very high precision what the gradients in the surface and gradients in the bed are in order to kind of quantitatively make inferences about the hydrologic network. So in 2013, 2014, the Center for Remote Sensing of Ice Sheets flew a radar campaign over the Cycle coast, these white lines through here. In addition, obviously, IceSat-2 bathed the world in its green light. As Knut said, this is the most garish figure I've ever made. That's the beautiful green light of IceSat-2 that has blanketed the Cycle coast. And so the question is, can we use our now kind of really high-resolution surface information, DHDT information, combined with cutting-edge radar techniques to re-image the region around Willans and perhaps better predict what the hydrologic system will do in the future? So I'm going to talk through a little bit of each of these two methods. Swath radar processing, which if you've heard me talk in the past, you've probably seen. And then the integrated altimetry over Willans that might help us get at this problem. So in a kind of conventional radar imaging system, you generate one of these radargrams, which you've probably all seen in the past, where your y-axis is your travel time through your wave, your x-axis is distance along the profile. And you use the sequential acquisition of information as you fly along to localize the reflections in space in the along flow direction. So you end up with this kind of 1D profile below you. But if your radar system has multiple antennas in the cross-track orientation, you can use phase information from your different elements in your receive array to localize information both in the along track direction and in the across track direction. So for every individual trace in a radargram, you can see what information is coming from the left, what information is coming from the right. And so as you fly along, you can produce, instead of just a single line of topography, like MacKie was talking about, you can generate one of these swaths of topography. So you start, much like multi-beam swath bathymetry, you can produce bed topographies that have comparable resolution in the along track and across track direction, kind of 20 to 50 meter resolution. So we're starting to produce these unprecedented pictures of the subsurface. I've presented the results from this analysis that we've done at Thwaites. This was using radar data collected in 2009, 2010. And these data are really powerful for understanding the interaction between ice and rock, the kind of stresses that are resolved at high resolution at the base of the ice sheet. But when I present this, usually I don't talk about the difference in quality depending on where you are in the system. So I'm going to run another animation in a second that's one of these sets of cross-track images. And on the right, the blue panel is going to show the cross-track images for this line. On the left will be the cross-track images for this. You can see that the dominant roughness in this grid is a cross-flow. Ice flows from right to left. So in this case, when you're flying along here, you've got a really rough surface to your right, a really rough surface to your left, and you can generate solid reflections back to your instrument. In this flight direction, you have a relatively smooth surface to your left and right, and you end up getting less information coming back into the system. So again, you can see the quality of your cross-track information is really high when you're flying parallel, well, when the roughness is in your cross-track orientation. So we were really excited about how well this data turned out for Thwaites. We thought we'd do it again at Willans, and we did the processing of the 2013-2014 data, and it turns out there is so little roughness in the bed that you can't easily resolve cross-track information with the swath algorithm. So while my abstract says I'm producing this beautiful seamless topography, the reality is I have this one single nadir reflection just like a normal radar. However, this does give you interesting, it's another piece of statistical information, just like MacKie presented, about the nature of the cross-track roughness. So we know Willans is smooth. We thought it was smooth before, now we really know it's smooth. So if we take that smoothness information combined with the nadir reflections, update the topography under the Willows ice stream, we can start to look at what the hydrologic routing in this region might be like. So I just distilled this down to some of the dominant water pathways if you assume the surface topography is REMA and you take our updated bed. And just like Sasha pointed out in his 2012 paper, there are kind of three dominant water pathways. There's this upper catchment that routes water across the Conway Lakes out to past the grounding line of the Lawrence Ice Plain. There's something that goes down through subglacial Lake Englehart down near this seismic area here, and then there's a central Willans catchment. And what I'm trying to do, and I'm just going to have to blaze through this, is figure out how the thinning pattern changes over time, whether or not it's stable, and whether or not we can make predictions about the changes in hydrologic pathways going forward. So ISAT2 is a great tool for measurement in the kind of 2000s, where you get 48,000 measurements within a 10-kilometer box per year. Cryostat2 gives you a comparable number of measurements that, when swath processed, give you really good coverage within a 10-kilometer box per year. And then if you add ISAT2 on, the scale changes by 3 orders of magnitude in the number of observations you get within a 10-kilometer box. And we can start to integrate all of these observations together to make predictions about the hydrology. So this is just 2 DHDT fields. This was produced by Helm et al. In 2014. And this is the DHDT field that Ben alluded to in his talk. And you can see that over the full ISAT1 to ISAT2 time period, the thinning pattern, thickening, red here is thickening, which is perhaps unconventional. Maybe should reverse that. You can see that the dominant thickening is happening on this true south, grid north area of the Willans Ice Plain. And that's been pretty consistent. Within the seismically active area, there hasn't been much change or maybe a little bit of thinning. And if you take the hydrologic pathways that we have given the observed surface, and we just assume that that thickening pathway is stable in the future, eventually, as things start to reorganize, you thicken, drive water further to the south. Oh, that's interesting. It did not get the last frame, the critical last frame, in which the hydrologic pathway that comes from Cam reconnects to the central catchment. And so there's a potential for additional water routing into the stagnating area of Willans kind of 30 years from now, if you have this kind of thickening pattern continue, that might actually facilitate the acceleration of the Willans Ice Plain. So a few conclusions. Willans is very flat. The thickening signal that we currently observe is really concentrated within the Willans Ice Plain, and that has the potential in the next 50 years to really redirect water flow in the region. Thanks.
Okay, thanks, Nick. Moving on. Now we have Neil Foley, who's going to tell us about electrical resistivity measurements from the McMurdo ice shelf.
The top half of my title should be there. Anyways, I'm presenting some fairly preliminary results, and so I think I will have no trouble sticking with a timeline, but in turn I would appreciate if anyone has any ideas for me, or questions, or avenues they think I should pursue, that they get in touch with me. Start this out, and I appreciate any input from the crowd. I've highlighted the sort of geophysical team that's working this, but I also work with an interdisciplinary team, and they bring a lot of expertise that I don't have. But right now I'm just going to be talking about the ice shelf themselves. Oh, sorry about that. Anyways, to start with the end, from the previous season, we did an airborne EM survey that covered the McMurdo Dry Valley's region. And this is the flight lines we flew over the McMurdo ice shelf from North Peninsula right there. We found brine in the McMurdo ice shelf. It appears to be sourced from the shelf edge and also subshelf fractures. And this is important for a variety of reasons. Big one, of course, is that brine can weaken ice shelves, which in turn are important for ice buttressing. And using EM is useful because it complements radar measurements. Instead of reflecting off of an interface, it allows us to actually image, in many cases, all the way to the bottom of the brine in the ice shelf. So that's useful. We used the SkyTemp system that's been developed at the University of Aarhus in Denmark. This is a picture of it flying over Lake Bonny. And this is a similar slide from my talk at TAM, if anyone was here for that. The things I want to highlight are that this system is capable of measuring the resistivity of the subsurface by inducing currents in it. And the important things to keep in mind are that there's a non-unique inversion that goes into this, and the data themselves that I'll be showing you are definitely preliminary, and we have to be aware of what the inversion brings into the images we create. But it is sensitive to salty water, along with metals, sulfides, and clays, but in this case, salty water is really what we care about. And like I said earlier, it's less attenuated than radar, so it's good for imaging through salty water. And so here's a map of a recent paper, the title of which was simply Widespread Potential for Seawater Infiltration in Antarctic Ice Shelves. It doesn't matter a ton what these bars are. There's sort of different thresholds of density at which seawater could intrude ice shelves. But the point is that there's a lot of the edge of Antarctica where the ice shelves could be infiltrated with brine, including in particular the McMurdo ice shelf, which this is the sort of lowest threshold for intrusion in the entire ice shelf. Has high potential for intrusion, and in fact, it's been measured there. For context, this is again Ross Island. The Ross Ice Shelf is right here. This sort of hatched stippled area is the McMurdo Ice Shelf, although I think more modern investigators would also sort of include it up to Nina Bluff. And people have been thinking about this for a while. This is from a paper that talks about the 70s. It's been studied before. Here's a much more recent image from Seth Campbell, where he did radar over the Andril site, including a huge swath of the McMurdo Ice Shelf. And this sort of shows a lava process didn't happen there. We can see a brine horizon. So this reflector is brine intruding from the shelf edge. It, in the radar, blinds us to what's beneath it. At a certain distance in from the ice shelf, you can actually then image the meteoric ice bottom. And then in detail, you can see that there are basal fractures, and you can even see the contact between meteoric ice and marine ice that's frozen on there. So there's a lot you can see in the radar. I'm going to switch to the EM, and before we switch to the results from the McMurdo Ice Shelf, this one is sort of use Taylor Glacier, which is maybe a familiar site if you saw Slavic's talk yesterday, for comparison. So this is a cross-section along this line. The colors indicate the resistivity on the log scale down here. And, just, and this will be the same scale for all the images. And what we see, of course, is the ice itself is quite resistive, but it's underlain by a relatively low resistivity zone. And, just for context, these reds are about 100 ohm meters. That's low resistivity. And blues and greens and yellows are even lower resistivity. And so this, I think there's a lot of evidence that suggests that there is a fair bit of salty water in this region right here. So this is just sort of the context when we switch to the ice shelf. And so what we're going to do is we're going to just take a swath across these lines. These are radial from McMurdo. And we're going to start with this one and work our way over to this one. And some of the things we're going to see, and I would love for you guys to tell me if you see anything else or have any ideas. But we can see, difference between sea ice and the ice shelf. That's a pretty easy thing to see. We can see infiltration from the shelf edge. We can also see what I think is infiltration from basal fractures, and potentially different saturations, either from ablation of ice or the migration of that brine along the fern-ice interface. And this is that really old map again, just to sort of give you a little bit of context. I just sort of matched up to show where the ice shelf sea ice interface is. It's rough. Anyways, so we're going to start with this line right here. And, first of all, big difference we can see, this is sea ice, this is the ice shelf. And this is also potentially, I think, ablated ice. This is a region where there's actually ice that ablates off and basically it decks up marine ice from beneath. And then, we can see marine organisms on the top of the ice shelf here. So I think that's potentially why this is relatively low resistivity. It's higher resistivity than the sea ice for sure, but we're still talking hundreds of millimeters, not thousands. Whoa. All right, well, that's one way to keep your time limit. I still operate. All right, let's go with this. We got it. All right, next line over, we can see intrusion from the shelf edge. It's possible that there's some basal ice frozen onto here. This is where we have to be aware of what the inversion is doing versus what's actually real. And then potentially maybe some of these areas where there's low resistivity far from the shelf edge, maybe that's a product of intrusion along the base of crevasse. It could also be that if you will observe that there's been sort of sutures of old ice in here. So this could be a former suture zone that's frozen back together. There we are. Next one over. Same story, we see a little bit of sea ice, we definitely see intrusion along the edge, and again we see some very distant from that interface low resistivity. And the ice here is still relatively low resistivity, but higher than what we saw at that area where we are aware that there's a high ablation rate that's affecting up probably marine ice rather than ice of meteoric origin. We go here, we see the widespread brine intrusion, and it starts at the shelf edge and travels kilometers in from that edge. And here's one where I think this is really nice, and this is where it really highlights the importance of bringing in electromagnetics as well as radar, because what we can see here is this to me really looks like we've got intrusion that then travels up and then maybe along an interface here. And this is something that would be particularly difficult to image with radar because it would probably just reflect right off of that edge. And what we can see there, though, is that it does terminate, and here we have some very high resistivity ice, and it's much thicker. And this is closer to the Ross ice shelf rather than the stuff that is sourced from the sort of landward area where there is higher ablation and it's just sort of more of a melange of stuff coming off of the coast. And so our last one here, this is good comparisons. This is proper, very high resistivity ice. It doesn't appear that there's any sort of convection up. It's possible it was frozen on marine ice onto here. This inversion obviously needs a lot of improvement before we can really draw a firm conclusion from it. But this is in striking contrast to what we saw over on this one, where it's thin and all of the ice is uniformly low resistivity for an ice shelf compared to, again, if we jump to the end. So just for one more for comparison back to the beginning. So I believe that is my conclusions. So just to summarize what I've seen, and again, this is preliminary, and I would really appreciate any input from anyone who has any good ideas or thinks that I'm barking up the wrong tree on any of these ideas. We see infiltration from the shelf edge, and I think also examples of basic crevasses. We're able to see beneath the brine. This can allow us to do some volume estimates. This can be combined with information from radar, perhaps satellite altimetry. I think it's possible there's frozen on basal ice. And I think this is something people have studied for 50 years now, so I think it's worth also sort of comparing with historical measurements to see if the extent of the brine infiltration has changed. And I think that also there's a difference between ice from near the Ross ice shelf, which is very high resistivity, versus ice that's sourced from nearby land and seems to be a combination of maybe ablated or sutured together ice that has fractures that were infiltrated. And so that's my conclusions, and again, I appreciate if anyone has any ideas, come talk to me.
Thanks, Neil. Up next we have TJ Fudge, who's going to be telling us about Cruz.
All right, thanks everyone for sticking around for the final talk. So my title is Prospecting for Gold, so drilling a deep ice core at Hercules Dome. So Hercules Dome is at the intersection of East and West Antarctica up on the ridge. And so it is a spot where we are going to drill a deep ice core, most likely beginning in 22-23. And so this is a spot where we want to kind of be right on the edge of West Antarctica in East Antarctica, to kind of look at what the history of West Antarctica was. And so kind of the main takeaways is obviously that the ice core drilling is coming. This past field season was a logistical challenge, but it produced some beautiful radar profiles that really cemented that we wanted to go here. And then we have got a great group that's really led by graduate students headed into the field in about another month. So the motivations for a Herc Dome ice core are to collect last interglacial ice, and which can either record waste collapse or the climate in which it remains stable. And so from the ice cores we've drilled, we don't have a climate record that really reflects West Antarctica in the last interglacial. So other motivations are we're getting more and more tools for being able to place temperature constraints on the LGM to modern temperature change. And this is still something we don't really know within about a factor of 2, and it can vary around Antarctica as well. And then something that the US Ice Core community has been kind of wanting for a long time is being able to look at how a glaciation begins. And so we just don't have ice from this kind of glacial inception time period. I'm not going to spend a lot of time motivating why the Hercules Dome core. Just wanted to illustrate this kind of one point using kind of a higher resolution climate model, looking at deuterium excess, and just how the change in topography, if you had a waste collapse, there's a significant response to that steepened slope, and Hercules Dome is in that location where we can see that. We've seen this in many other model results for the water isotopes and many other characteristics. So Hercules Dome is not a perfect dome. So we kind of have this strange structure. This is the ISAT-2. Nick produced this. And so it's kind of a complicated area to go explore, and that's where the kind of prospecting for gold is coming from. So looking for that ideal ice core site. And so the 30 days of camping out at Hercules Dome last field season turned into 2.5 days being ferried from South Pole by Twin Otter. And so the coverage was not as what we would have liked, but there are some couple new radar lines here near where the ITAS traverse came by in 2002. And then also over here on what we call West Dome, speaking of kind of the grid directions rather than true directions. And so I want to start with West Dome, recognizing that this actually represents a fairly large area, so about 70 kilometers between them. So pictures of the radar setup and the radargram that comes from that. And so what you can see is beautiful, clean layering, tracking the bed. We've got a nice divide. The divide itself is offset just slightly from the bedrock high. We can do some depth age modeling, which puts our last interglacial ice at about 50 meters above the bed, where we can image continuous radar layers. We're not very afraid of basal melt here due to the shallow ice thickness, which is about 16 to 1800 meters depth. And so we're trying a lot of different things to understand Hercules Dome. A lot of this is still very preliminary because we don't have many data constraints from it yet, but we intend to get those over the next couple of years. And so this is Andrew's kind of initial runs for Elmer Ice to really try to model it, to look at what the surface velocity kind of system is around the Herc Dome complex. We're also using flow line and flow band models to look at the internal layer structure, which is relatively simple, but isn't matched perfectly kind of using the modern accumulation gradient. And this, of course, will be much more refined once we have surface velocity measurements. We have end glacial velocities with PRES and much more characterization of the region. We're working on getting towards inferring a temperature, kind of following on Winnie's talk, and so using the attenuation rates and seeing what fits with the temperatures. And so there'll be much more of this work, which is being led by Ben, which also can help us hopefully constrain what those basal temperatures are. So kind of the summary of the West Dome radar profile is that this is a good site for a deep ice core. We would prefer a deeper site. And so this would have a thicker packet of Eemian or last interglacial ice. It would also allow for borehole thermometry. So borehole thermometry is one of our best techniques at looking at temperature change in the past. We're developing other new tools, but it'd be nice to be able to have a deeper site. there definitely are deeper sites around. And so if we look over here at the new East Dome profiles, we can see that these were not collected over at least a simple kind of ridge system. And there's also a lot of complexity within the internal structures. And so drilling into here, even though it's deeper, it's probably not going to be our ideal ice core site. But there is a lot of area left to explore, and this coming field season is really going to focus on this area between West and East Domes, in addition to revisiting West Dome, and we've got 2 field seasons coming, and so we're excited to have both of those seasons to be able to get those measurements that require 2 field seasons of occupations, specifically PRES and velocities. So a lot of different radar work. I know that it makes Canute happy to have more radar systems going into the field than there are field members. So that's a good sign. And I just want to conclude with, we are beginning the planning process for the ice core. So there's going to be multiple planning meetings held in the coming years. These are probably going to begin next spring. The goal is to attract a diverse, and when I say diverse, I mean scientifically and demographically, group of PIs for the project. So we haven't made really any decisions about where these meetings are going to be held, except to say we're not going to hold them on the back end of, say, the South Pole Ice Core meeting, because we want to reach a broader community than who are already working on ice core problems. And so it is our intent that the details of these will be shared with multiple communities, including kind of this WAIS community. And so I've had a few conversations about how to become involved, and I'd love to have more input from all of you on how we can reach a diverse group. And so with that, thank you.
Thanks, TJ. And let's have all the other presenters for this session go up.
And can I also have any other student evaluation slips? Do you have them? Okay.
All right. Questions? Do we have another mic floating? Question in the back.
This one's for Woody, actually. I was curious what potential there is for. I really like what you're doing, and was curious what potential there is to use the internal layers in some of that radar data to even refine some of the reflectivities to get better strain control on the temperature.
Sorry, Sasha, can you repeat that?
Sorry. Yeah. Oh. There we go. All right. I don't need a shot, do I? Okay. So, I was curious what potential there was to use internal layers in some of that data to even get a better internal strain model for the ice for geothermal heat, to back out geothermal heat. Because I like what you're doing with that. Yeah, that waste divide. But yes, I was curious what the next step was. I guess.
Yeah, waste divide is actually pretty hard because there's a lot of the echo-free zone layer is actually pretty thick. So like the furthest the layer could go, it's like 2/3 of the ice column. So that's your biggest limitation right there. But I think with some of the work that like Duncan have shown and Nana and Nick that are going to do as part of the architecture project, where they're actually tracing the layers and trying to do some clever interpolation among places where we don't see them, that would be the first step to being able to extract more information in addition to temperature, but also vertical strain based on those layers tracing in that area.
Awesome.
This one's for Mickey. I'm curious, as a sedimentologist, I like looking at samples. I like being able to hold something, look at it, and make observations. So I'm wondering how far into the future, what would you need to be able to start differentiating between different bedrock units? because if anyone's ever looked at a bedrock map of Antarctica, it's pretty blank. And as we continue to look at samples and try to make sense of where it's coming from, we can then help your community as well as kind of like constraining where things come from underneath the ice.
Yeah, I mean, that would be the dream. I think to do that, I would need, a lot of geophysical data from different platforms and a lot of repeat surveys with them, so I can start training them on each other. And then also, lots of observations from outcrops, so we can actually start to constrain what material we have nearby.
I think this is broadly across the board, but the approach what are your approaches for dealing with the inherent uncertainties in the radar? As Lava was saying, radar lies. I love radar, but radar lies. What are your approaches for dealing with those, and especially when thinking towards combining different measurement systems?
I think that radar is an incredibly powerful hypothesis testing tool, and so if, as an exploration tool, you're struck with all these uncertainties because the quality of end glacial or subglacial reflections depends a lot on a number of different properties. And so if you go into a problem with a hypothesis about temperature variability, as an example, the radar data can be used to test that. There will be other sources of variability in the data, but you should have consistency between, well, you can search for inconsistency between the data and your hypothesis more easily than you can tease out all of the individual contributions. So the more that you can use auxiliary data sets or models to set up a desired observation by the radar data, you can go seek that out in the data. The inverse problem is more complicated, I think.
Yeah, I totally agree with Nick. I think if you combine different type of techniques, both coming from the radar, from the numerical models, but also different kind of geophysical techniques, then this problem becomes a lot more solvable. For example, for the temperature problem, there's only so much you could expect the GHF variation, could vary across a certain time, certain length scale, and so the ice thickness. So by combining the numerical model to give you that 2D information, you should be able to limit the uncertainty, or sort of rule out some couple of scenarios that your radar try to lie to you about. And I also think there's a lot of potential, for example, what Chloe and what Slavic have shown and what Neil have shown about the potential of using magnetolytics and all the other geophysical instruments, and thinking about moving towards joint inversion of all these different geophysical instruments to get a much better constraint on the temperature and ice flow and etc.
Other questions?
Yeah, this one's for Neil. I think you probably know about the Rosetta project, which just collected 3 years of data over Ross ice shelf, and I think there's been some really nice data there for you to look for your signals that you're after. I'm sure you know, but I just want to make sure.
No, thank you. I appreciate it. It's a new project for me, so any kick in the right direction is better than stumbling randomly. I guess I have a question for the table full of people who are much better at radar than I do. I kind of whispered this to ask Nick to make sure it wasn't a totally crazy question. Which is, and this is sort of related to the previous question about how can we use radar and whether or not Nick's answer was that it was a good hypothesis tester. And so my question for you folks is, to what extent is using multiple frequencies of radar with the same measurement help you? When is it useful? What are the technical considerations? I've only sort of just dragged a radar across a glacier. You guys have done much more complex things with it.
I can whisper my answer back to Neil. I mean, in a lot of ways, frequency gives you another free parameter to start testing for variables that you are otherwise under constrained problems. But there have been historic efforts to combine multiple frequencies to make inferences about internal layering that have yielded inconsistent results. I mean, Olaf Eisen has spent a lot of time trying to really break down what makes an glacial reflection, and by looking at multiple frequencies in different systems, he's finding that sometimes the response of one system is very hard to relate to the response of another one. So, as with all problems where you're solving for an unknown, the more parameters where you have controlled variance, the more information you can tease out of the data. But historically, those efforts have been a little bit limited in their ability to make deep inferences.
Yeah, I think different frequencies are also able to resolve different scales of roughness at the bed. My group can correct me if that's wrong, but having the multiple frequencies is useful because you can see different types of bed features, but then you can use that to compare different observations from different systems, which we do have, and right now it's very difficult to do inter-system comparison. So that's a very enabling tool.
Other questions from the audience? All right, let's thank.